So we are going to learn, hopefully we have like a good idea of if we understand function or not and evaluate. That like CFU that you just did is going to be its own test topic when we get to our Unit 2 tests. It's just going to be like being able to determine function or not and evaluate. That's it. So if you just rocked and rolled through that CFU, like you should be feeling good. You're understanding that. Don't forget it because it's still a couple days before we get to our test, but hopefully that test will be a good time for you. The next half of this unit is about domain and range, and we're going to we've got a lot of notes. We're just going to kind of see where we land, and then we have more time next class to finish up here because domain and range is a big topic. Y'all did that Desmos thing. Most of y'all did that Desmos thing last time, and kind of we're starting to see how it works. But it's different. It's a different way of thinking. It's conceptual, so it takes a little bit of time, especially when we get into the word problems with it. So we're just going to kind of go for it. We're on page 8 in our notes. We'll see how far we get, do some Delta math practice, and then we'll have ourselves a 4-day weekend, right? Well, y'all will. We'll have a 3-day weekend. We got to work tomorrow, but it's all good. It's what we do, okay? So again, this is a huge thing. We were just talking about being in Algebra 2. We're doing this in Algebra 2. It's not going away. It's not going to go away in pre-cal. Anytime you talk about functions and graphs, you need to be able to know how to do their domain and range, okay? It's different, but just hang with me and let's try to get some good definitions at the beginning. I'm going to make some notes, put some stars by stuff like, hey, this is how we do it, and then we're going to jump into the practice. Okay, and that's really how you're going to be able to catch it and learn is just doing practice on your own. But I kind of got to guide you through what we're doing right now. So first vocab word is domain. Have you seen that word before?
Yes.
In middle school?
Mm-hmm.
Yes? Okay, I know if you did the Desmos thing, it talked about domain. But your domain is all inputs, which we learned and we reviewed last time. The inputs are X values. That's very important. This is a test-taking strategy. Anytime you see domain, you are thinking about X's, okay? STAR test will do multiple choice stuff, and they'll ask you for the domain, and they'll have answer choices with Y in there, and we throw them out because we know it can't be right because domain has to go with X. So it's what your domain does is it tells you, hey, these are the X's that this function has, that it goes through. These are the boundaries, and that's you're going to hear me say that a lot. Domain and range is all about boundaries. That's why I gave y'all those purple pens, because when we get to graphs, we're going to be making boundaries, and I want y'all to have different than your pencils. So I'm going to let you use a flare pen for that.
Does
you're
everybody know what a boundary is? Are we good on what boundaries mean?
Yeah.
What's a boundary?
Like mathematically.
Just anything. Just boundary. What does the word boundary
I
mean?
think it's kind of like, okay, if you think about it, like if you have something and then
they were giving you that shaded region, and you were kind of moving it around to say, hey, my graph's going like this. And you were setting the boundaries like it's happening in this region, in this boundary, from this guy to this guy. And that was your domain. And then your range was your boundary vertically. Okay, so that's what we're doing. We're finding like big picture. We aren't going to harp too much about what's going on inside, but it's like what's the leftmost point and the rightmost point, okay? And again, yeah, think about sports. Think about your field and stuff like that. So the direction is really important. So I want y'all to remember this. When we talk about our domain, we have to go from the left to the right. Okay? You have to start that way. Your inequalities should always be going from least to greatest. We're going to write that down here. But you're looking at the x-axis, which is this one. This is your x-axis. And you're going through. Can y'all see that okay? I need to get a different color. I was trying to be like Wakeland, cheering for Wakeland today, but it's kind of showing up weird on my iPad. So I'll use red. Yeah, I record my lessons. Okay, so you're looking at your x-axis and you're listing your boundaries from the left to the right. Okay, that's your x-axis right here. So when I draw these boundaries in, I'm going to be drawing vertical lines that are cutting through my x-axis. And I'm looking at what x value is happening there. But the key is that you've got to go from the left to the right. Okay, that's our domain. Let's talk about the other one. What's the other word?
range.
That's your range. Range, it's a very similar idea. It's still your boundaries, but it's your vertical boundaries. It's talking about what y values are going on in the function, and the direction is bottom to top. Bottom to top. Okay, and you're looking at your vertical ones, your y-axis. And you've got to go in the correct order. Some of you guys, I think I actually had someone in each class in here that when you were typing in your range on your Desmos thing, it wasn't working because you had like the bigger number first and the smaller number second. So you've got to have that order least to greatest. So I'm going to put a note right here. Must be least to greatest.
Write that down, it's important.
Least
to greatest.
Least to greatest. And that kind of takes care of the, if you forget like left, right, bottom, top, least to greatest is going to help you figure that out, okay? The lower number than the higher number on the X and on the Y, okay? So there's multiple ways that we can talk about domain and range depending on what type of function we have. So we've got two big ideas. Our main goal is to be able to take a graph, a situation, a table, a whatever, and write the domain and write the range. But we have two different types of data that we're going to look at. And so we need to talk about these words and what these mean, okay? So the next vocab word is discrete. Have we heard that word before? No? Yes? Maybe? We don't know? Well, guess what? We've got definition for it right here. So discrete domain and range are when only specific given or reasonable values can be included. So I think the easiest way with a graph, these two graphs down here are discrete. Why? What's different about? Because it's dots. Discrete graphs will be dots. They're just individual data points. You don't know anything about what's being connected with them. So if you see a graph and you're like, hey, I know this is a graph, but there's no line, there's no curve, it's just dots, that's going to be discrete. Discrete is dots, okay? In a word problem, because we're going to talk about word problems, and y'all, this is like the hardest part about domain and range, is you've got to first figure out, is your situation going to be discrete or continuous? So what I always think about is if I have my story, I'm like, all right, can I have fractional amounts? Can I have decimals? So if I'm talking about, I'm going to go to the concession stand. I'm at the freshman football game, and I want to go to the concession stand because I'm hungry. And I'm going to go up there. Am I going to be able to say, hey, I want 1.5 Snickers bars? No. What are they going to say? Well, you can have one or you can have two. So that would be a discrete example because I can't have between 1 and 2. Okay? Just not going to work. So that would have to be discrete. So if I were to put that on a graph, I can have 1 bar, point. I can have 2 bars, point, 3 bars, so on and so forth. Okay? So that would be a discrete situation. So examples of discrete situations, again, are like, I don't know, we'll put snacks. What about people or animals? Can you have half people, half animals? No. So if you have a situation where you're talking about the number of people that go to the football game, you can have 1 or 2 or 3 or whatever, but you can't have those little decimals in between. So that classifies a situation as discrete. And we've got 2 word problems here that we'll kind of talk through, but we need to know what that means and know that word. So let's actually go down here and look at these examples, and then we'll come back to our continuous. And we want to write the domain and range of, we'll start with this one, this discrete graph. We know it's discrete because what's on the graph? Dots. Just dots. Okay, that's the first thing we got to tackle. Now, when we write our domain, let's answer this one first. Is this a function?
Yes.
Yes.
Why?
Yes.
Because it passes VLT.
Good. It passes the VLT. Let's write that down first. Okay? Now we got 2 parts. We're going to write the domain first, and then we're going to write the range. With discrete, I think this discrete data is a little bit easier when it comes to writing because these are individual points. which means your domain and range are just going to be a list of numbers. So let's do our domain. What is domain always talking about? X's or Y's? X. I'm going to write that underneath. Domain is talking about my X's. So I'm going to go through and I'm going to say, all right, here's my graph. Here's what X is. My graph went through. Now, we write this as a set. So watch how I do this. I'm going to draw a squiggly bracket. It's called a set notation. It's just squiggle a little bracket. Okay? It's not going to, it doesn't have to be pretty. Sometimes that's not a very good one. So just give it a little squiggle. It's not a parentheses because it's not an ordered pair. And we're going to write least to greatest, left to right. What is the first X value that my graph took on? 0. So I start with that. I already have my vertical lines on here, so this is helpful. What was the next X value that my graph took on?
1,
Next.
2,
2,
3, 4, and 5. Do I have any other values in there?
nope.
Close it off. We're running into the other problem. Okay, so that's how I write my domain. I just look at my picture. What X values happen? Do I have a dot at 6? So do I put 6 in my domain?
no.
No. Okay. Do I have dots in negative X's? No. So I just start there. Those are the only X values. So what do you think you're going to do for your range?
Check do it with a Y.
Left.
What'd you say?
The biggest
Left.
number.
Check the left.
Check the
Why?
Y's. Yes. Check the Y's. Okay. And again, bottom to top. So I'm going to draw through the Y axis here. What's my lowest Y value? 2. Y value was 2. Do y'all see how I'm drawing through these Y values to help me see what numbers I'm going on? That's why I gave y'all. If you have that purple pen, use a purple pen. What's the next one? 3. Next.
4,
Then
5, 6, and 7.
good. Close it off. Okay, so it's just a list. I draw all over my graphs when I do domain and range, and that's why I gave y'all the flare pen. I think it's helpful, especially when we have discrete. I'm drawing lines, and I'm always drawing down to the axis that I'm talking about. With domain, I was drawing to the x-axis because these are the numbers that I care about with domain. These are my x's. With my range, I'm drawing over to the y-axis because those are the numbers that I care about. Okay? Try this one, the discrete graph right below. We know it's discrete because it has our graph of dots. So you're going to do your squigglies. Domain talks about x's, range talks about y's. List them out. Tell me if it's a function. Elements do I have in my domain? How many numbers were in there? 5. Okay, and what were they? Least to greatest. What was my domain?
0,
-1 actually came first. I had a -1, then 0, then 2, and 3. That's my domain. Okay, we get that? Thumbs up. Very good. All right, what about my range? What's my lowest y value?
2 ones.
1. Now, how many points were on this y value of 1? 2 of them. But we only have to write that y value of 1 one time.
Oh.
Okay? If you wrote it twice, that's okay. I wouldn't count that wrong. You don't have to erase it. It's fine. I wouldn't count that wrong. But there happens to be repeating y's. Does that mess up being a function? Repeating y's? No. So this is still a function because what can't repeat in a function? X's. But if you do have repeating anything, even if you have repeating x's and you're doing the domain, you only have to write that value one time just to save yourself some time. What's my next y value?
2.
2, then 3. Do. So you just have to write those there. Let me see if we have any of those on there. Let's do a word problem. Are we ready for our first word problem? Okay, so remember, when we get to a word problem, really when we get to anything, we have to look at, is it discrete or is it continuous? Okay, so let's read our situation. Remember what I said about words. You got to think, can I have like fractional pieces of things? So we're going to a football game. stole my example. With your friends, you invited 13 people to come with your group, but you aren't sure who's coming or not. If you are for sure going and the number of people in attendance is represented by X, what would be a reasonable domain? Okay, so we're talking about domain, which means we're talking about what values? What always goes with domain? X. And they told us, I know I wrote over it, but they said the number of people is represented by X. Okay, so we are going to list how many possible people can come to the football game with our group. Does that make sense? I know that from the problem. That's what it tells me. Now, I know I'm for sure going. So what's the least amount of people that are going to go? One. So I'm going to start. This is, it's people. So we have to be discreet, right? We can't have half a friend. So I'm going to make a note that this is discreet right here. So I'm going to set up my squiggly brackets. And we said the least amount of people, because I know I'm for sure going, is 1. What's the next amount of people that can go? 2.
All the way up to 13 like this.
How'd you, we'll use dots, but how'd you know 13 was your upper boundary?
Because you invited 13.
You invited 13 people to come. So 1, 2, 3, ... I'm okay if y'all use ... because we don't need to write every single number between then. And we invited 13 people, plus ourselves. So what's really the boundary? 14. And that's your domain. Now, the reason it was discrete, we're not going to have half a friend. So we have to list it like that. And it's just, these are the possible amounts of people that can come with us through the gate. Ourselves, and then potentially all 13 friends. And anywhere in between. We okay? No? We're tired. Okay. Well, I'm sorry. All right. You guys try the next one. This is talking about grades. Okay? Grades are represented by Y. We only give whole number grades. Okay? You're going to want to use ... here. Please do not write out all these numbers. Read the situation. Try to find the range. Story. We're talking about grades. It says the total grade is represented by Y, and we're trying to find the range, and range always has to do with Y. So we're listing the possible number of grades. Okay? Grades has to be discrete because they said we don't have, we only give whole number grades. We don't give halves. Okay? So, what's our boundary? What's the lowest grade that teacher gave? 32. So that's what I start with. 32. What's the next highest grade that someone could get? 33. 34. ... What's the highest grade? 89. Yeah, I definitely don't want you to write those out all the way. So I think writing domain and range with discrete data, I think, is fairly easier than with continuous because you're just listing. It's just a list of numbers. Continuous is a little different way to think because we've got some inequalities. There's not a example of a table or ordered pairs on here, so we're gonna go to the back of our packet where there's some blank space, and we're gonna do just some bonus problems that I think are gonna be really helpful for you for your test, okay? Y'all trust me? So let's call it a bonus problem.
You just do it on the back of your packet.
Back of your packet. I'm sorry, there's not more space. Okay? We're going to do 2 bonus problems. So, flip to the back. All right, number 1. We're going to find domain and range. And we're going to do ordered pairs. Okay? So ordered pairs are in parentheses. Let's do 3. 3 ordered pairs. Daniel, give me a point. Your favorite 2 numbers.
3 and 2.
3 and 2. Okay? Cruz, give me a point.
1, 7.
1, 7. Miles, give me a point. Give me a negative.
-2 and 3.
Okay. Perfect. So here are ordered pairs. I'm going to put this set around it because sometimes the STAR test will do that. If they have multiple ordered pairs, they'll kind of do like a set of these guys. okay? I just don't want that to freak you out if you see that. But basically, I've got 3 ordered pairs here. Now, with ordered pairs, or the same thing with tables, we don't know that these points are connected. So when the points are not connected, it would just be a graph of dots. So is this going to be continuous or discrete?
Continuous.
We don't know that they're connected. So this is going to be discrete. These are just going to be dots. Discrete. I'll write that in case you're wondering where that came from. Okay?
Don't you like add them all up and then divide them by like how many numbers there is?
That's range.
It's range.
Not the domain and range we're talking about. You might be talking about averaging or something, but no, remember, domain and range is just saying, here are the x's that are happening. Ranges, here are the y's that are happening. That's all. It's just a list. There's really not calculations that we're doing with this. And for some people, they really like that. For some people, they don't. So here's our domain. We'll start with that. We agree that it's discrete, so we're going to use our squiggly brackets. Domain has to do with what values?
Exit.
Your x's. So I am going to underline my x's. X is the first number. I'm just looking at the first number in the point. And all I have to do is list it, but I got to put it in order. Least to greatest. What's the smallest x value?
-2.
-2. Next.
1.
+1. Next. 3. Close it off. Pretty easy, right? With the range lists the y values. Let's circle those. And this is what I would do on my test. I'd do something to differentiate between those two, so that way it's telling my brain, hey, I'm looking at the underlines. I'm looking at the circles. Okay? Least to greatest. What's our smallest y value?
1.
2. Y values. Circles. Oh, did you miscopy that? 2. What's my next? 3. And then my next is 7. All right, was that bad?
Yeah.
That was bad? Well, I hope it's not, because it's definitely a star-worthy question. Okay, I'm going to give you one more bonus problem I want you to do. Find domain and range. And then we're going to switch gears to continuous. We're going to get started on that. I'm going to give you a table this time. Nick, give me a point.
1, 2.
1, 2. Mohammed, give me a point.
8 and 10.
Braden, give me a point.
Can we get negative?
Yeah.
-10 and 5.
Zane, one more.
Oh, -10 and 6.
Okay. Is this a function?
No.
Why not?
X repeats.
X repeats. All right, find the domain and range. It's discrete. We don't know anything about these connecting. So we're going to talk about in a minute. So find the domain and range. Make sure you put it in the right order. You got it.
It's 1, 8, -10.
Okay, we want to go least to greatest.
-10.
You are correct. You are talking about these are your domains. -10. Now, how many -10s are there? How many times do you have to write it? Once, okay?
And then 8. Oh, 1 and 8.
Very good. -10, 1, and 8. I always want y'all to do it in least to greatest order. Okay, so please get in that habit. You only have to write -10 one time. If there's ever a repeater, you don't have to write twice. I'm not going to count it wrong if you do, but the STAR test is only going to put it in there one time, so I don't want that to throw you
I
off.
thought we did that on one of the other problems.
This one's not asking about, is it a function or not a function? So it's okay just to write what the domain is.
Yeah. Because we're going to do domain and range of things that are not functions. And you're going to see it too on the next page if we make it that far, okay? So that's a big idea, and so I'm probably going to ask you, is it a function? But we can still give the boundaries, all right? What's the range?
2, 5, 6, 10.
2, 5, 6, and 10. Very good. Okay? All right, fun bonus problems. So go back to those because you're going to see that, and it wasn't in the notes right there. All right, let's take a 3-minute brain break, and then we will go back to page 8 and talk about continuous. All right, so we've talked about discrete. We've done examples with discrete graphs, which are dots. We did some word problems because we can't have half people and half grades. And then we did our bonus problems with some ordered pairs and a table. Now we're going to talk about the other type of domain and range. And to be honest, this one is really more what you're going to see moving forward with graphs. And Nick, please sit up. With graphs and different functions in your future math. Okay, so this is a big deal. We're going to get to a good stopping point. I'm going to let you guys make sure you kind of can get through your Delta Math for today. So we'll just kind of hang tight and we're going to continue this next class, okay? So if it's not like totally sinking in today, it's okay. So the next type of domain and range, or the next type of situations we're going to be looking at are continuous. That's our next vocab word, continuous. Continuous domain and range are when all the values in between your boundaries can be included, okay? So you have your boundaries there, and your graph is connected. This is the key word here. Continuous means it's connected. Okay, so if you look at a graph and it is not just dots, it is a line, it is a curve, there may be an arrow or two. That is continuous, okay? Continuous is connected. Say it. Continuous is connected, okay? So when we look at our graphs and we have to determine which one is which, we're seeing are the points connected. And that means we're in a continuous situation. We are going to talk about word problems. Again, the word problems are kind of tricky. So if we have a continuous situation, real world, we have to think about where's something that I can have all the decimals in between. It's not like when I went to the concession stand, I can only get 1 Snickers or 2 Snickers. I want to talk about when can I have all those in between. Any ideas?
Nope.
You still can't have all the values between 0 and 1. Time. Right now. All the time's passing. You know, like if you look at a timer and it's just constantly going and going and going and going. We don't go from like 0 minutes to 1 minute, right? We have all those milliseconds in between. So time is an example of something that is continuous. So if we have a problem and our X is talking about the number of hours, we got to represent all the tiny decimals in that chunk of time. Driving. Y'all don't drive yet, but you ride in the car, right? Okay, when you get in the car, have y'all ever watched the, what's the thing called?
The odometer?
Yes. And it's just like constantly going, okay? Because you're not just going like 1 mile to 2 miles. You're going all the distances in between.
Oh, the little I don't know what to call it, the steps that lead the excavator, what's it called? Elevator. It's like the thing that you just like step on at the mall.
Escalator.
Oh, an escalator. Yeah. It's constantly, yes. So time, what did I say? Distance. At the gas pump, y'all ever watch a gas pump? I've been watching that because those gas prices, man, I'm like, oof, here we go. Okay, but you can see all those numbers going and going and going. They don't just have like chunks in between. So those would be examples of continuous situations. And again, the word problems are tricky. That's why we got a day and a half on it. But we'll try to get one done today. Okay, we have a different notation when we talk about domain and range with continuous data. With discrete, we did the listing. Squigglies, list, because we could go through and we could say all those numbers. We can say all these X values right here. But when we have something that all the values in between, we can't list every single decimal in between. So we use an inequality to represent that domain and that range. Okay, so y'all remember inequalities, right? Less than's, greater than's. So kind of back to when we were solving with the open dot and closed dot, and y'all saw this on the Desmos thing. If you have an open dot, they did not take the extra ink to fill in that circle on the graph. It happens sometimes. They just give it to you that way. Do we take the extra ink to fill in the less than or equal to?
Yes.
You don't take the extra ink to fill in the dot. You don't take the extra ink to do the sign. So you will use just a less than. Majority of the time, there are cases you can use a greater than, so I'm going to write it down now. But most of the time in this unit, we're just going to be using less thans. Okay, so no line. Open dot means no line. What about a closed dot?
It means the line is
There means there. I'm going to draw an open dot right here and a closed dot for you. So we will use less than or equal to's. Again, there will be a time where we use greater than or equal to's, but we'll get there later. Okay, so our big ones are going to be just the less than or equal to. That just depends on the problem. That just depends on the setup. You're going to see different ones. Delta Math is going to give you different ones. They could be one open, one closed, whatever. Okay? So kind of keep that in mind. That shouldn't be too crazy because we've kind of already practiced that before. But we also are going to look at graphs, and I don't know if we'll get there today, but we're going to look at graphs that have arrows. Okay? That means that your graph goes on forever in the positive direction or the negative direction. So y'all know the number that represents forever? Infinity. So if you have an arrow on your graph, you'll either be going towards positive infinity if you're going right, because positive infinity is our right side on our x, or up, or we could also be going forever to the left, which we use negative infinity. Okay?
Wait,
Oh, I thought infinity it doesn't matter.
If we're going in the, like, to the left, we want to say we're going in the negative direction, so we call that negative infinity.
I can't draw infinity.
Turn your a sideways A, or do two circles. Just two circles. Okay? We will never reach infinity. Okay? You won't. So if we have infinities, we will only use a less than here. Only use a less than with an infinity. We won't ever equal it. So an infinity is kind of like an open dot. There's not an endpoint, but you're never actually going to get that there.
But can't infinity equal anything?
Infinity is like, it's not an exact number. It's like an idea. Like, it just means it keeps on going and going and going. You're never really going to get there. Okay? But that's what we use to represent it goes forever. Okay? There's not a boundary if you're going towards infinity. Okay? There is kind of a template. There's no room in these packets. A template that we're going to use for domain and range when we have discrete. Okay? So I'm going to try to fit this right here. Domain and range. So when we have a continuous situation, I'm going to draw a line through that. When we have a continuous situation, we know the graph's connected. We're going to kind of set up our framework, okay? So here's what our framework looks like. We're going to start all this using less thans, just because it's easier to learn it this way. So you are going to leave a space after domain. Here's your template. Less than, domain always talks about what? X, less than blank. Leave a space. Okay, so there will be two blanks there. Y'all okay if I actually put a blank right there? So when you recognize that something is continuous, I want you to kind of put this down. Less than X, less than. And then you can look at your picture and you go and fill in your boundaries. Where is the leftmost X value? That's a number, and you're going to put that number right there. And then you're going to say, okay, is it open or closed? And I'm going to put an equal to or maybe not. And then I'm going to say, all right, where's my right boundary? And I'll put that number right there. So when you fill these in, you will have numbers in there. Number and number. And what that means is, hey, this graph has got stuff going on in between these two X's. Okay? It can be just a straight point. It can be whoop-de-doo-de-doo. Who cares? That's what's happening there. And then range, what's nice about this is it's pretty much the same setup except for what goes in the middle. With range. Y. And you put your lower and upper boundaries, and those will be numbers. Remember, your domain goes left to right. Your range goes bottom to top. I'm going to put a big box around that because this is a really big idea. Okay? And that's how we fill it in. So it's going to be probably less writing than discrete, because discrete, you're like counting. But it's going to be a little bit different way to set it up. All right, y'all want to try some?
Yeah.
Let's try some. Flip over. It's cold in here. All right, let's try to do, we're going to do this one. We're going to do this one. This one, and this one. How about that? 4 problems. And then I'm going to try to let y'all delta math it up. It'll save us some to kind of warm up with after the long weekend. All right. We're going to start with this graph right here, this first one, this little line segment. This is continuous Y. The 2 points are, what's the word? What's the word? Connected. This is continuous. Continuous. Okay? So I'm going to set up my framework for domain and range. Domain, because it's continuous, I'm going to put my less thans, what goes in the middle with domain. Range, I'm going to put my less than. Range, I'm going to put a y. I'm just going to set that up. That's the first thing I'm going to do on this problem. We're going to do that on the other two graphs too. All right? And then I need to go in and find my boundaries. If you have your purple pen and you want to draw on your graph, let's do that. Okay? Now, domain boundaries are the leftmost x value. Can I find a left boundary on this graph?
Yes.
Draw it in. What x value did we draw through?
No.
What x value? It's a number. What x value is this? X value 0. It's a closed circle. Good job. I know you got it. Closed circle. So what do we have to put under here? Under this guy.
A line.
A line. Because it's closed. So
Equal.
0 is less than or equal to. 0 is included in there. What's the right boundary?
5.
Draw it in. Positive 5. Closed circle. So what do we do?
Draw a line.
Draw a line. And that's it. This says, hey, here's my boundaries. 0 to 5, we got stuff going on. Okay? The graph is doing whatever. But all those, the line between all those points mean that all those values are on my graph. Okay? Range. Yes?
So, what do you mean by like closed circle? The circle's like on the graph that
This-
that are closed.
The circle, look at this. Look at this one right here.
Oh, that's
Open versus closed.
All right.
It's like filled in. Okay? All right. With range, here's the thing with range, guys. You're going this way. You're going this way. You have to go least to greatest. So is there a lower boundary?
2.
Okay, good. I'm going to draw a line. I would honestly do my boundaries on my paper before I write anything down. So my lowest y value was at 2. Is 2 actually included? Is it equal to? Is the circle closed?
Yes.
Yes, so put an equal to. And then my upper boundary is
7.
positive 7. Is it equal to included?
Yes.
Is this guy a function?
Yes.
Yeah.
Okay. I want you guys to try this one right here. I know. I might take one off. Fine. You want to try the curvy one on your own?
Yeah.
All right. Find the curvy. Try the curvy one on your own. Y'all convinced me. It's about to be a long weekend, so fine. We don't know if we're ready for it. See if you can at least do your boundaries. If you don't fill in your inequality, that's fine. But at least do your left and right boundaries and draw it. No, draw it on your paper. That's why I gave you that pen. And then do your bottom top boundaries. Yes. When I'm done. Can you put boundaries on this graph? Yes. So there's my left and right boundaries. Even though this guy's curvy in there, does that matter? No. Okay? So what is my leftmost x value that's going on? 0. But what kind of circle is that 0? So do I put an equal to here? No. We just leave it. Okay? Perfect. 0 right there. Now, my right boundary. 1, 2, 3, 4. Not negative. It doesn't matter that it goes down. We're talking about the x's right now. It's at positive 5. But the circle is closed, so I put a line. So that's what's a little bit different about doing domain and ranges. You're looking at the x's, the y's. What's your lowest y value? Did you count it? 1, 2, 3, 4, negative 5. This is the negative 5. This is the lowest point of the graph. And it's closed, so put a line. Okay? What about your upper boundary?
0.
Is 0 the highest point on this graph?
4.
Draw it on your paper and count it up.
4 or 5.
1, 2, 3. Well, we got to know.
4.
It's 4. Okay? So it doesn't necessarily have to go endpoint to endpoint, but is there a defined circle at the little top, at the little maximum right here? Is there a defined circle for you? No. So here's what we do. If we don't have a defined circle, we assume that it is actually touching there, it's actually equaling there, it's closed, so we need to put a line. Okay? So you should really, there are some exceptions, which we'll get into when we learn some different types of functions. But for right now, unless the circle is open or unless it is an arrow, you should be putting a line underneath your stuff. Okay? So that goes with that. Is this guy a function? He's different. He's curvy, but is he a function?
Yes.
Bless you. He's still a function. Let's do one with arrows, and then we'll do one word problem. Okay? Write the domain and range. All right, y'all see how this graph has arrows going on, right?
Not a function. I already
Why is it not a function?
because it passes.
It
The
does
gradient
fail,
passes
so-
vertical line.
It doesn't pass the vertical line test. So we'll say no, and we'll say fails the VLT. Okay? Domain and range. Let's set it up. It's continuous because it is.
Arrows.
The arrows don't define it being continuous. These were continuous, so they didn't have arrows. What's the key word?
Infinite.
Connected. Connected. Not just dots. It's connected. Okay? There are arrows. So we are going to involve infinities. So let's set up our domain with our less thans. What variable goes in the middle of domain? Variable for range? Y. Okay? All right, we're going to do domain first. We need a boundary. Can you find a leftmost boundary on this graph? Can you draw it in? Yeah, so that's 0. Now, what did I say? If you can't see an open circle, what do you assume?
It's closed.
It's close, so it's going to equal 2. Now, these arrows, I sometimes draw them off the page like this. Can you find a right boundary if there's arrows or
Infinite.
one arrow?
Infinite.
It's going forever in the positive direction, which is
Infinite.
infinity. Infinity. So I'm going to put an infinity right here. And we never equal infinity, so I can just write that. Okay? Even if one of the arrows, there was only one arrow, and there was another endpoint, it's still going on forever in one place, so you got it, that arrow's going to trump an endpoint there. Okay? The range on this one is a little bit tricky. All right? So we know we're pointing this way, right? But range is talking about vertically. Yes, we're going right forever, but this bottom little piece right here is also going down and over, down and over, down and over, down and over. And there's an arrow. So can we find a boundary at the bottom?
It's infinite.
It's infinite, but it's in the negative direction.
Negative.
So we have to put negative infinity. We will never equal infinity. What about the top guy? Where is it going? Up and right, up and right, up and right, up and right. What's up?
Negative. Positive.
Positive infinity. Okay? Negative infinity to positive infinity. This is the same thing as all real numbers. Negative infinity to positive infinity. It means everything. There's a lot of functions we're going to study that have all real numbers. All right, let's go to Delta Math because I don't think there's word problems on Delta Math today. Just so you guys can practice with this, your Delta Math, it's pretty much mostly continuous. Yeah, I'll pick up the purple pens. Let's see what we got. Log in.
What time do we get out?
30. We got 15 minutes.
We got out at 30? I thought we got out at 25.
Nope.
No, can I go back?
That's just
Oh, we still on activity.
That's just on Wednesdays. No activity scheduled today. Okay, look, I want you guys to try to get done these 2.2 questions. Are you looking? There are 4 and then some individual ones. These individual ones are star questions, so they're really good. So let's make that our goal is to get those 6 questions done today, and we'll pick back up next time, okay?